Now, of the simple process scheduling algorithms that we sort of ask you to simulate with charts and by manually with charts and diagrams like I've been showing in these videos, round robin scheduling is the most complex. That does not mean that it is the most complex that's used in computer systems. Computer systems have process scheduling algorithms that go far beyond these simple examples. These simple examples, though, give us a good mental model for understanding what it is the operating system is doing, so that if you're looking at the code or you're trying to understand how operating systems actually work, you can think of them in these simple models, and that helps you to understand the more complex code and implementations actually used by the operating system. The round robin scheduling algorithm, our goal is to enable interactivity. That is, each process never waits for very long. Each process will run as soon as it can while letting all the other processes run as well. So we limit the amount of time that a thread, that a CPU can have at any one moment in time. We have what we call a time quantum. A time quantum is a basic amount of time that the operating system gives a thread or a process before intervening and running some other process. Sometimes called a time slice, and it's typically some value between 1 millisecond to 100 milliseconds. It used to be that Unix systems always used a time slice of 10 milliseconds. But in more recent Linux systems, that value can be configured and it can be changed, and can sometimes even changed dynamically in various ways. But it's generally some value between 1 millisecond and 100 milliseconds. If you use less than 1 millisecond, then the operating system is spending too much time switching and not enough time actually running the processes. And if you use a time slice that's a lot bigger than 100 milliseconds, then we don't have enough interactivity, and the system tends to be kind of jerky, and people start noticing lags and other problems with the operating system. Now, an operating system uses a timer interrupt to actually cause one process to stop, to get a signal, and to signal to the operating system that it should stop the running process, make it ready, and find another ready process and run that ready process at that time. The time quantum is a period of time that may be smaller or larger than the scheduling quantum. It all depends as to how the operating system and the hardware is configured to run. So here's round robin. With round robin, we know that the first process is going to run for the first 2 time quantums, because it's the only process that's ready during that time. But each one of these time quantums here is available for any ready process to be run at any time. So what we'll see is the operating system, after those first 2 time quantums, will tend to try to run a different process on every single step, according to the round robin, and according to the order in which the processes arrived. So it will keep a ready list like this, and initially, process 1 is the only process in the ready list. But at time quantum 2, there are 2 processes, and process 1 is already run, so it will then go around the list and it will run process 2. And then it will run process 1, and then process 3 arrives, at which time there are actually now 3 processes to be run. Also at time 4, process 1 finishes, so there's really not 3, there's only 2 processes to be run. So then I'll run process 2, then process 3, then process 2, gotta get this right. Then it will run process 4, which has now arrived in the ready list. And then it will run process 3, then process 2, then process 5, which has now arrived, then process 4, then process 3, 2, and so on as it goes along and all of the processes are run until they're completed. And at the end, process 4 is the only process in the system, so it will be given multiple time quantums until it finishes. And so with round robin scheduling, we end up with a schedule that looks like this, where during each time quantum, or at the end of each time quantum, the operating system will make a choice among all running processes to decide which one gets to use the CPU next. And it'll do that in a round robin turn-taking fashion. You calculate the delays and the turnaround times like this. You see that some processes can be delayed quite a while but the delays don't occur at the beginning, they occur throughout while it's waiting for other processes to run. So delay does not, in this case, indicate that the process took a long time. It indicates that there were a lot of other processes in the system that needed to be shared, that the CPU needed to be shared with at that time. So the effectiveness of round-robin scheduling really depends on the number of threads, the number of processes in the system, and the size of the time quantum. As we see, process 2 has to do a lot of delay because there are a lot of threads, a lot of processes in the system. Sorry, I use the term threads and processes sometimes interchangeably. When I say threads, you just sort of have to hear me say process because sometimes I get that wrong. It also depends on the size of the time quantum. So if the time quantum were infinite, then we would get an algorithm that's essentially the same as shortest job first. And if the time quantum were infinitesimal, then we'd have a system that's doing nothing but context switching and changing processes all the time, and would probably very rarely ever get to actually run the processes themselves. A large number of threads means that the time between the scheduling of a single thread increases, meaning we get slow responses. But a larger time quantum means that the time between the scheduling of a single process also increases. So we get slow responses as well. So smaller time quantum means higher processing rates, but also means more context switching overhead. That means that the operating system has to run more frequently. And that's something that we don't want. We want the operating system to run to be in the background as much as possible.